In this session, you're going to know how to calculate the gravitational field strength G in a radial field. You'll be able to calculate this gravitational field strength using G equals negative big G m over r squared, and you'll understand the importance of the r squared in the formula and explain the difference this makes to your results and graphs. You'll be able to explain what happens to the field strength when we head towards the centre of the Earth. For electric fields, we'll know how to calculate the electric field strength E in a radial field. We'll be able to calculate the electric field strength using E equals 1 over 4 pi epsilon naught times Q over r squared. And again, you'll understand the importance of the r squared in the formula and explain the difference this makes to your results and graphs. And you'll be able to explain what happens to the field strength as we go towards the centre of a charged sphere. The strength of a field, both electric and gravitational, depends upon both the size of the field generator. As you can see, the larger the mass or the charge, then the stronger the field, and the distance the mass or charged particles are from the field generator in a straight line in meters. As you can see here, the closer you are to the field generator, the stronger the field. We can measure the strength of an electric field using a flame probe. Chris is going to demonstrate this for us. Cheers, Chris.
Right, this is an experiment to measure electric field strength at a fixed point in space around a charged sphere. Our charged sphere is a football covered in tin foil suspended from the roof by 3 pieces of string. This is an EHT, a high voltage supply, and this is a gold leaf electroscope. The positive cable from the EHT is connected to the charged sphere. The negative cable and the earth is connected through the earth port of the gold leaf electroscope at the bottom here. Here I've got a pole with a syringe attached to it, a gas supply in the end of the syringe, and a wire wrapped around the needle leading to the top of the gold leaf electroscope. What I'm going to do is the gas is running through the needle, and I'll light it at the end of the needle. Here the flame ionizes the air around the needle, causing free electrons to flow without any interference of charged metal ends. So when I put this flame near the charged sphere, what we're going to see is, on the gold leaf electroscope, when I turn on the voltage, and as you see here, the gold leaf is now deflected away from the main plate. And as I move the probe away, the deflection becomes less. Now by this, and many different calculations, you can work out the field strength via the deflection and the change in height.
Cheers, Chris. As we've seen in previous lessons, Newton's law shows us that the force between two masses can be found by F equals minus big G m1 m2 all divided by r squared. And we also know that the gravitational field strength in a uniform field can be found by G equals F divided by m. If we combine these formulas, then we can see that G equals negative big G m1 m2 divided by r squared all divided by m, which ends up as G equals negative big G m over r squared. In exactly the same way, we can find the electric field strength in a radial field. Again, from earlier lessons, we know that we can find the force between two charged particles using Coulomb's law. F equals K, Q1, Q2, all divided by r squared. We also know that the electric field strength in a uniform field can be found by E equals F divided by Q. Again, if we combine these two formulae, we can find that E equals K Q1 Q2 divided by r squared all divided by Q, which ends up as E equals K Q all divided by r squared, where K is a constant. K equals 1 over 4 pi epsilon naught. So to find the electric field strength in a radial field, we use E equals 1 over 4 pi epsilon naught times Q over r squared. Why not try these exam type questions to test your understanding so far? Now sketch a graph of your results showing how the strength of both the gravitational and electric fields in a radial field vary with the distance r.